and in this video I will discuss with you application of work energy theorem and conservation law of mechanical energy. Hello students, I am Sumit, a physics faculty at Toppers Academy, and in this video I will discuss with you application of work energy theorem and conservation law of mechanical energy. So we will see some examples here, how to apply work energy theorem in a given problem. Okay, so what is work energy theorem? First let me write what is work energy theorem. So work energy theorem is that for a given system, in a given system, if there are in a given system work done by all the forces, that is work done by the conservative forces, work done by the non-conservative forces, and work done by the external forces in a system, that is work done by all the forces, this is equal to the difference between the kinetic energy. Okay, that is, if a system was having initial kinetic energy as Ki, and after some time it is having kinetic energy Kf, so this work done by all the forces, that is conservative forces, this is work done by the conservative forces, work done by the non-conservative forces, and work done by the external forces on the system. External forces that will be equal to the change in kinetic energy. Change in kinetic energy of the system. So let us see how to apply this theorem in doing some problems. While solving some problems, so let us say there is a problem given to you, and in this problem there is a ball which is having a mass 5 kilogram, and this falls down from a height 10 meter. From a height 10 meter, it touches the ground with a speed. Okay, so this is its initial velocity, that is u. Okay, and it is falling from the rest, so its initial velocity is 0. And let us say when this is touching the ground, that velocity is v, and it is equal to 10 meter per second. And it is equal to 10 meter per second. There is air friction present here. Air friction is present. Air friction is present here. So now the question is, what is the work done? What is the work done by air friction? Okay, what is the work done by air friction? Okay, so how I will solve it? So here, what are the forces that are acting on this ball? One is its weight, and as it is falling down, that air friction, it will work in the upward direction. So this is force due to air friction, and this W is its weight. I can write that W is equal to what? W is equal to mg, that is 5 into, we are taking the value of g as 10 meter per second square. Okay, so if I put value of g here, so what I will get? I will get 50 Newton. Okay, I will get 50 Newton. Now, when this ball has touched the ground, okay, it starts from this height h equal to 10 meter and it touches the ground. So in that process, during its motion, its displacement is, what is its displacement? Its displacement that is equal to what? Or I can write this, let me write this, force due to gravity. Okay, that weight is actually force due to gravity. Force due to gravity. Okay, now what is the displacement of the ball? That is 10 meter. Okay, 10 meter. I'm only talking about their magnitude. Okay, now what is the work done by the gravity? That work done by the gravity is equal to mg into s. Okay, and it is of what kind? This work will have a positive sign, as force and displacement, they both are in the same direction. Okay, and what will be its value? That value will be equal to 50 into 10, that is plus 500 joule. That will be plus 500 joule. Okay, now what is initial kinetic energy of the ball? Initial kinetic energy of the ball. That is the initial kinetic energy of our system, right? And that is equal to what? 1 by 2 m into initial velocity, that is 0. So 0 is square, and this is equal to what? This is 0. What is final kinetic energy? Okay, that is 1 by 2 mv square. And as it touches the ground with 10 meter per second. 10 meter per second. So that kinetic energy after reaching the ground, that is kinetic energy final, that will be 1 by 2 into m into 10 square. So that will be equal to 250 joule. Okay, this calculation, that will give me 250 joule. Okay, and kinetic energy is always positive. Okay, so now use the work energy theorem. What is the work done by the gravity? So here only two forces are present. One is its weight, that is force due to gravity. Another is that air friction. So work done by air friction, that will be equal to the change in kinetic energy. That will be equal to the change in kinetic energy. So work done by air, if I put the values, what is the value for work done by gravity? That is 500 joule. That is 500 joule plus work done by air friction. That will be equal to what? That will be equal to 250 minus 0. So work done by air friction, that will be 250 minus 500, 250 joule minus 500 joule, right? So that will be equal to minus 250 joule, and you can see from here that it is a negative work done. That is, air friction is opposing the motion of the ball. Okay, now suppose I want to do the same problem using the conservation of mechanical energy, using the conservation of mechanical energy. And we know, what does conservation of mechanical energy states? It states that Ui plus Ki, that is sum of potential energy plus kinetic energy, remains constant. That is Ui plus Ki is equal to Uf plus Kf. The sum of potential energy and kinetic energy, that is known as mechanical energy. But can we apply here this mechanical energy, this conservation of mechanical energy, can that be applied here? No. This law only valid in presence of conservative forces, okay, only valid in presence of conservative forces. But what is happening in this example, this gravitation force, okay, that force due to gravity, that is a conservative force, while this air friction, so force due to gravity is conservative in nature, while this air friction that is non-conservative in nature. Non-conservative. So we cannot apply the principle of that conservation of mechanical energy here. Okay. Now let me do one more example. And suppose now there is a ball, this is same ball, okay, and I am considering that it is having a mass of 5 kg. It falls from the rest from a height of h equal to 10 meter. It is falling from the rest from a height of 10 meter. Okay. Now if your problem is find out with how much velocity it will touch the ground. So I can solve this problem using both methods, that is work energy theorem and conservation of mechanical energy. So first is using work energy theorem. Work energy theorem you can always apply, okay, in any case. So it is a more general form, right? So what is the work done by gravity here? That from the previous problem I can write that it is equal to plus 500 joule. Okay, there is no air friction and no other forces are working here. So I can write that this work done by the gravity, that will be equal to the change in kinetic energy. Okay, in previous problem we know that velocity with which that ball was touching the ground, but here that is unknown, right? That is unknown. So let me take that velocity is v velocity with velocity, this is the velocity of the ball, at the ground. Okay, so that kinetic energy at the ground, that is kinetic energy final, that will be equal to 1/2 mv square, and this kinetic energy initial, that will be equal to what? That will be equal to 0 as it is falling from the rest. Now if I put this expression into this and value of the work done by gravity, what I will get? That I will get 500 joule, that is equal to 1/2 mv square. Okay, and that v square will be equal to 500 into 2 divided by m. M is given as 5 kilogram. So that will be, that v square will be 200. Okay, if I will put 5 here, that will only 100 will remain here, okay, in the numerator. So I can write that this velocity, that will be equal to 10, magnitude of the velocity, that will be equal to 10 into square root of 2, that is 14.1 meter per second. Okay, if there is no air friction, that much will be the velocity. Okay, now if I want to do this similar problem using conservation of mechanical energy. So the first question is, can we apply this conservation law here? Okay, can we apply this conservation law here? As all the force is present, and that is the only force present here is this force due to gravity, right? This force due to gravity. Okay, and that is always conservative. So I can say that only conservative forces are present here. That means if only conservative forces are present here, that means work done. That means this conservation of mechanical energy, this principle can be applied here. Okay, so I can write that Ui plus Ki, that will be equal to Uf plus Kf. Okay, Uf plus Kf. Here this Ki is initial kinetic energy and this is final kinetic energy when ball reaches the ground. Okay, so I can write that Ui, what will be Ui? That will be mgh, as it is above the ground. So I can write it will be mgh, and that will be equal to 5 into 10 into 10. That means 500 joule, right? That potential energy of the ball at that height from where it is falling, that is 500 joule. Okay, at that point. Okay, what will be kinetic energy at that point? That kinetic energy initial of this ball, that will be 0 as it is falling from the rest. Now what will be the potential energy when ball reaches the ground? That is 0. We are taking it as a reference level, right? Now what will be Kf? That is kinetic energy of the ball at the ground. That will be 1 by 2 mv square. I am assuming that v is the velocity of the ball when it touches the ground. Now using conservation of mechanical energy principle, I can write that Ui plus Ki, that will be equal to Uf plus Kf. Okay, what is Ui? Ui we have calculated, that is 500 joule. Initial kinetic energy is 0. Final potential energy, that is potential energy at the ground level, that is also 0. And this kinetic energy at the ground, that is 1 by 2 mv square when it touches the ground. So again we are getting that 1 by 2 mv square, that will be equal to 500. If I put the values, so what I will get? If I put m equal to 5 kilogram, then I will again obtain that this v square, that will be equal to what? That will be equal to 200, and this v, that is magnitude of the velocity, that will be equal to 10 into square root of 2. That means 14.1 meter per second. So we are getting the same result. So in this way we can apply work energy theorem in a given problem. The only difference between these two is between work energy theorem and conservation of mechanical energy, that work energy theorem is a more general form. So it can be applied in the presence of conservative forces as well as in the presence of non-conservative forces. But that conservation of mechanical energy, that can only apply when there are conservative forces present. Okay, thank you.